All right, in this next section, we're going to take a look at multiple representation of acceleration through the use of equations, constant acceleration equations, through the use of data tables, and through the use of position, velocity, and acceleration versus time graphs. Let's take a look. It says each exercise gives you either a position versus time equation in the form of x equals of 1/2 at squared plus v naught times t plus x naught, or a velocity versus time equation in the form of at plus v naught. Now, please note that earlier in the notes, we wrote both of those equations as follows. We wrote them as x equals x naught plus v naught t plus 1/2 at squared. Realize this is a quadratic equation, so all we did here was write it with the squared part first, and then the t term, and then the constant. So that's the way we just chose to write it backwards, okay? And then same thing with this here. This equation for velocity was given to you as v equals v naught plus at. But again, we wrote the t term first, and then the constant. So just know that those are the two equations from earlier written in reverse order, okay? For each exercise, fill in the number blanks in the equations, then make a table of positions, velocity, and acceleration, then plot points that represent your table on 3 of the given graphs and create a motion map. Okay, so there's a lot of stuff we have to do with this, all right? Here it goes. So we're going to do equations, table, graph, and finally motion map. Motion map is the one where we make the dots and then put the arrows, things like that. Let's take a look at this one. This is going to take a while, so please make sure and pause or rewind the video as you need to, okay? Because there's a lot going on here. First things first, I'm going to rewrite the equation right above this, and it's x equals, well, here it is. Here's the equation. X equals 1/2 times 4 plus a negative 20 plus 50. Now check out what I did here. I took the equation down here and I just substituted into the parts. The term, oh, I forgot to write the t squared, sorry. T squared, and then t. So the term in front of t squared is the 2 here, but according to the equation, it's supposed to be 1/2 times the acceleration. So 1/2 of 4 is 2. I'm just writing it this way. Minus, I chose to write it as plus a negative, so I can take a look at what my sign of velocity is. And then my constant value of 50 is at the very end. All right. Now what I'm going to do is I'm going to fill out my position values, okay? And here's what I get. I'm starting initially, if I plug in 0 for here and 0 for here, you can see I just end up with x equals 50. So at time equals 0, x equals 50, okay? So we're kind of starting there. Now, if you also look at the equation for velocity, this one here, this is final velocity, this is initial velocity, that's acceleration, and that's time. So according to this, you can see that since the equation is supposed to be 1/2 times at squared, you guys can see that what number is following 1/2? It's 4. So 2 is not my acceleration. I have to rewrite 2 as 1/2 of 4. 4 is my acceleration. So I'm going to jot that down. Acceleration is 4 meters per second squared. And I can rewrite that equation here as v is equal to at, which would be 4 times t, plus v naught. Now, look at the equation one more time. The term in front of t in this equation is also v naught, which is my negative 20. So it's 4t minus 20. So what we're going to do is we're going to use both of these equations here to fill out this chart and this chart. Okay, let's try it. If I plug in 1 in place of t here and here, We go 1 squared. 1 squared is 1 times, and then half of 4 is 2, minus 20 times 1 plus 50. And we can see that this is 2 minus 20 is negative 18, plus the 50 would be 32. Okay, if I plug a 2 in there, well, I'm going 2 times 2 squared, which is 4, minus 20 times 2 plus 50. Well, we have 8. 8 minus 40 is what? Negative 32 plus the 50, we're looking at 18. Okay, and we just keep doing this. And if we do this for all the other values of 3, 4, and 5, we end up with, we plug in for 3, t equals 3, we get x equals 8 meters. At t equals 4, x is 2 meters. And when x is 5, we plug in 5, we actually get 0. Okay, now doing the same thing for velocity, right? At time equals 0, if I plug in 0, so 4 times 0 minus 20, you can see velocity equals negative 20, right? There's our first value. I'll do a different color for velocity. Negative 20, okay? Now if I plug in 1, 4 times 1, 4 minus the 20 would be the negative 16. When I plug in 2, 4 times 2 is 8, minus the 20 is negative 12. I hope you can see we're dropping the velocity by 4 meters per second every time. So you can predict the next one's going to be negative 8, then negative 4, then eventually down to 0. Okay. And we have an acceleration of 4 meters per second, and it's constant, right? It's constant because we have only one value of acceleration. And it's not changing with respect to anything. So acceleration is 4. Should have written it here. I'll do that in a different color as well. Change this up a little bit. So this is 4 all the way down. So yeah, the acceleration was 4 meters per second squared. The velocity was 4t plus a negative 20. Okay, so now let's fill out this portion right here. So for each one, circle for each one. Velocity is what? Positive or negative? Well, the velocity for the most part is in the negative direction until finally it stops. So the velocity is negative. The acceleration, on the other hand, are positive values. Okay, and we're gonna find out why graphically when we put this. So when we graph this, we've got our scale right there. At we have a point at 0.50, at 1.32, at 2.18, at 3.8, at 4.2, and at 5.0. And so our graph looks like this. And as you can see, what are we doing here? We are decreasing. We have a decreasing slope, so we are going from steep to flat, which means we're slowing down. Steep to flat curve means you are slowing, but you're slowing with a negative slope. You're slowing in the negative direction. That is overall positive constant acceleration, which we have right here. That's awesome. Now, this positive constant acceleration needs to translate to a positive slope. So we know that for the velocity initially at time equals 0, we have negative 20. And at 5 seconds, we have 0. And so we end up with a linear situation, just like this, where the positive constant acceleration here is that slope. The slope of a velocity graph is the acceleration. So that slope is the positive constant acceleration we're dealing with. Okay, and then how do I plot the actual acceleration of 4? it's going to be a constant value of 4 right across all the way. Okay, now how do I begin to plot the motion map of this thing? Well, I'm slowing down. So anytime I'm slowing down, my acceleration vector needs to go opposite my velocity. Now, my velocities are negative. They're going to the left, I guess you would say, and they're starting at time equals 0, they're starting at 50. So I'm going to make a dot at all my locations. So I'm going to make a dot at 50. I'm going to make a dot at 32 right here. I'm going to make a dot at 18, which is right here. I'm going to make a dot at 8, which is right here. I'm going to make a dot at 2. Okay, and then finally 0. Okay, so I got that. So 1, 2, 3, 4, 5, and then 6. Okay, so what does my motion map look like? My velocity looks like this. Notice my velocity vectors are pointing to the left because it's negative velocity, but they're getting shorter because I'm slowing down. But since I am slowing down, my acceleration vector needs to go the other way. And it's going to be constant acceleration the whole time. So I'm going to write constant acceleration. Notice my acceleration arrows are the same length because they're constant, but they're pointing to the right. Right would be the positive direction. So there would be my motion map for situation number 1. Number 2, we have x equals 125 minus 5t squared. So we should rewrite this as x equals negative 5t squared, write this t squared term first, plus 0t. You need a v naught t section there, because remember the equation is this. It's x naught plus v naught t plus 1/2 at squared, and we rewrote it as 1/2 at squared plus v naught t plus x naught. So I need a v naught term, and if I don't have it, it's 0t. Plus the 125 we see right here. So just rewriting it like this. Okay. What are my terms? Okay, I should be able to write this as 1/2 of negative 10 t squared plus 0t plus 125. Now, what does that help me with? Over to the side, let's write some values here. Acceleration is going to be the term after 1/2 and in front of t squared. So acceleration is negative 10 meters per second squared. Velocity, the initial velocity is the term in front of t, and acceleration goes here, so it's negative 10t plus v naught. But my v naught term is 0, so negative v naught t plus 0 is the equation I'm working with in this instance. Let's plug in some values here, see what we got. At time equals 0, if I plug in 0 for this, then I've got x is equal to negative 5 times 0 plus 125. So that means at time equals 0, x is at 125 meters. If I plug in at 1 second, then we're looking at negative 5 plus a 125, which would be at what, 120? Then if I keep going with this pattern here, plug in 2, so negative 10 plus that would be, now we're down to 105, right? You see the pattern here. Negative 15 and oh, I'm sorry, I forgot to square. So it's 9 times, so let me back up. So 2 squared is 4 times the 5 is negative 20 plus the 125 is 105. That's how we get that. Then the next one would be what, 3? So 3 squared is 9 times 5 is 45. So negative 45 plus the 125 would be what, 80? Right? And then we have 4. 4 squared is 16 times 5 is 60 plus the negative 60 plus the 125 would be, what, 45, right? And then if I put 5 in there, well, 5 squared is 25 times negative 5 is negative 125. So negative 125 plus 125, right, adds up to 0. So that's what's going on with that data there. The velocity data, same thing, but I'm using this equation here. And since I don't need to write the 0, it's really negative 10 times t. So at t equals 0, velocity equals 0. So this object starts from rest. At time equals 1 second, negative 10 times 1 is negative 10. At 2 seconds, right? Why did I write negative 2? Sorry. 2 times negative 10 would be negative 20, and so on. You can see it's increasing by negative 10 every time. Very easy pattern. And the acceleration is again constant at negative 10 meters per second squared for the whole time. Okay. If we look at what we're working with here, velocity starts with 0 but ends up increasing in the negative direction. So velocity is once again negative, but then again so is acceleration. Acceleration is negative here too. Let's go ahead and plot this. So at 0, we're at 0, time equals 0, 125 right here. We're at 1 second, 120 right here. We're at 2 seconds, 105, we're right here. 3 seconds, we're at 80, we're right here. 4 seconds at 45, and then 5 seconds at 0. And you can see the position time curve is sloping to the ground like that. And we're going from a flatter slope to a steeper slope, which means we are speeding, but you're speeding with negative slopes. You're speeding in the negative direction, guys. This is negative constant acceleration. Right? A positive and a negative combine to give you a negative. Well, how do I plot this in the velocity scale? Well, I've got to start off with 0 for my initial velocity at time equals 0. And then at 1, I'm at negative 10, right? 2, I'm at negative 20, and I just keep going all the way till 5 seconds when I'm at negative 50. And I have a nice straight line, the slope of which is my negative constant acceleration of negative 10. And then I plot my slope of negative 10 as constant acceleration down here. All right. Since I am speeding up, velocity and acceleration point the same way. Remember, when they slow down, when an object slows down, velocity and acceleration vectors point opposite ways. But when an object speeds up, acceleration goes the way velocity does. So let's see here. The object is starting at 125. Way over here. The object starts at 125 at rest. Right here. And then the object's at 120. Then the object's at 105. Right here. Then the object's at 80. Then the object is at 45, then the object is at 0. So the object is doing this. It starts off from rest, so I have no velocity vector to start with. Then all of a sudden it gains velocity, so notice the velocity vector arrows are getting longer and longer because we're speeding up, right? We're accelerating in terms of speeding up. My velocity and acceleration vectors need to point the same way, and my constant acceleration vectors are going to be the same length because they're constant, and they're going to point exactly the same way that my velocity vectors are pointing. Okay, that's the situation number 2. In situation number 3, we've got x equals 10t squared. So if we're looking at the equation of 1/2 at squared plus v naught t plus x naught, what does that tell you? That x is equal to 1/2 times 20 t squared, because 1/2 of 20 is 10, and then plus 0t plus 0. Okay, so initial velocity is 0, acceleration is 20, meters per second. So this would be 20t plus 0. Okay, let's fill this out. 10t squared, so x equals 10 times t squared. So at time equals 0, right, position is 0. At 1 second, 1 squared is 1 times 10 is 10. At 2 seconds, 2 squared is 4 times 10 is 40. At 3 seconds, 3 squared is 9 times 10 is 90. At 4 seconds, 4 squared is 16 times 10 is 160. At 5 seconds, 5 squared is 25 times 10 is 250, would be the first column. The velocity data would be completed by filling out velocity equals 20t, 20 times t. So I'm going to fill in these values. So with time equals 0, velocity 0. Whoops, wrong color. Okay, now at 1 second, 20 times 1 would be 20. At 2 seconds, 20 times 2 would be 40. At 3 seconds, 20 times 2 would be 60. And I think you get the pattern. We're increasing by 20 each time. So the next one would be 80, right? And then 100. What does this tell you? You're increasing positive acceleration, positive constant acceleration, increasing by 20 meters per second every second. So the positive constant acceleration of 20 the whole time. Okay. Now my velocity starts at 0 and they're all positive after that. So that would be positive velocity and positive acceleration. Plot your values. At time equals 0, x equals 0. At time equals 1 second, we're at 10 meters. 2 seconds, we're at 40. 3 seconds, we're at 90. 4 seconds, 160, a little above 150 there. And 5 seconds, we're at 250. Look at what we have here. We have a nice quadratic. We have a nice parabola drawn here, just very sharp. So we're going, a curve is going from a flatter slope to a steeper slope. Okay, what does that mean? Flat to steep. It means the object is speeding up, but ladies and gentlemen, it's speeding up with positive slopes. So if you're speeding up, which is positive in the positive direction, that's positive constant acceleration. So let's plot that. We're starting with velocity 0, that's right here. And at 5 seconds, we're at 100. So there's our velocity graph. And that positive constant acceleration is the slope of the line of the velocity time graph. Okay, now the acceleration would just be that slope happens to be positive 20. So we would plot that as a constant acceleration for 5 seconds. Okay, now since we are speeding up, your acceleration and your velocity go the same way. Okay, since we're speeding up. And it's going to start with 0. So plot all your positions. So we're at 0. Just plot your positions here. 0, I'm at 10, then I'm at 40, then I'm at 90, then I'm at 160, then I'm at 250, right? And so start from rest, so no arrow. Then my arrows will get longer, like that. Okay, those are my velocity vectors. Okay, getting longer and longer. And my acceleration vectors should be constant. I'm making them really long because I've got a large acceleration of 20 and they're pointing the same way. Okay, in the next situation, we're given x equals 10t minus t squared. Let's rewrite that. Well, first of all, that would be negative t squared plus 10t. Okay, something like that. Now, plus 0. So if we write it with respect to the actual equation, x equals 1/2 at squared, 1/2 acceleration times time squared, plus v naught, initial velocity times time, plus initial position x naught. What we see is x equals 1/2 times, well, 2, negative 2, t squared, plus 10t plus 0. Okay, so what that tells you is the acceleration is negative 2. So start there. Acceleration is negative 2 meters per second squared. So I'm going to write negative 2t right here. And the initial velocity is 10. So I'm going to write that there. Okay. Now what we're going to do is we're going to plot the points for the first 5. So if I go 10 times t minus t squared, well, if I plug in 0 for both, I start with 0. Okay, so I start with x equals 0. 0, 0, everything 0. But if I start with 1, well, 10 squared is 10 minus 1 squared is 1. I get 9. If I plug in 2, 2 times 10 is 10 times 2 is 20, minus 2 squared is 4, right? I get 16 when I subtract them. 3, 10 times 3 is 30, minus 3 squared 9, I get 21. 4, 10 times 4 is 40, minus 16. 40 minus 16 is about, what, 24? And 5, 10 times 5 is 50, minus 25 would be 25. So the difference in the positions is getting smaller and smaller. Kind of tells me we're slowing down a bit right there. Velocity-wise, well, negative 2 times t. So negative 2 times t plus 10. So at time equals 0, that's 0. My initial velocity is 10. So I start there. Then if I plug in 1, negative 2 plus 10 would be 8. When I plug in 2, negative 2 times 2 is 4. Negative 4 plus that would be 6. And you can see I'm decreasing by 2 every time. So the next one, of course, will be 4, 2, and 0. Because I am dropping 2 meters per second every second. That's what this means. I am decreasing by 2 meters per second every second. That's what constant acceleration is all about, ladies and gentlemen. It's either increasing or decreasing your rate of acceleration, your rate of change of velocity, the same amount every single second. Okay, you can see your velocity, even though your velocity is decreasing, they're all positive because you're going in the positive direction. So velocity is positive. The acceleration, however, is negative. All right, let's plot our position points. We're going to start off with x equals 0, 0, 0. We're going to go 1, 9. We're going to go 2, 16, like this. We're going to go 3, 21. We're going to go 4, 24, and we're going to go 5, 25. And we get ourselves a nice curve that looks something like that. And when we examine this a little closely, we have a slopes that change from steep slopes to flat slopes. And anytime you're going from steep to flat, you are slowing down. And we're slowing with positive slopes, though, so we're slowing in the positive direction. This is overall going to be negative constant acceleration, as we see. Negative 2, in fact. Our velocities, we start with a velocity of 10. We end up with a velocity of 0 at 5 seconds. And our slope would look something like this. And the slope of that line would be our negative constant acceleration of negative 2. Finally, we plot that negative acceleration as a constant negative horizontal line for 5 seconds. Okay, now plot your positions. We're at 0, 9, 16, 21, 24, and 25. And so our velocity vector will look like this. It's going to get shorter and shorter. Because again, what are we doing? We're slowing down, right? So your velocity vector is getting shorter. And since we're slowing down, velocity and acceleration have to go in opposite directions. So my acceleration's smaller, it's 2, so I'm going to draw much shorter vectors for acceleration, but I'm going to draw them all the same length. and they're negative. They're going in the negative direction. They're going left. That's my acceleration. And that would be my motion map for scenario number 4. Now in situation 5, we have x equals 50 minus 10t. So here, notice we don't have a t squared term. So this would be 1/2 times 0t squared plus a negative 10t plus 50, if we rewrite this to look like this. And that shows you that your acceleration is 0. I'm going to write a 0 in front of the a, because remember this is v equals at plus v naught, right? And then acceleration is 0 with an initial velocity of negative 10. So the initial velocity is negative 10, but it's not just initial velocity, it's constant velocity because you're not accelerating. So you're not accelerating, we are moving with constant velocity in the negative direction. Okay, CV stands for constant velocity. So let's go ahead and plot this. So we're going to go x equals 50 minus 10 times t. So at 0, 10 times 0 is 0. We start at x equals 50. Then we put a 1 in here, and then we're at 50 minus 10, which is 40. Then we're at, put a 2 in here, 50 minus 20 is 30. And you can see we're dropping, we're moving back from 50 seemingly all the way to 0. So 20, right, then 10, then 0. We're dropping 10 meters, right, every second. We're moving with constant velocity, so a constant velocity of 10. So it's negative 10 the whole time. Okay, whoops, I messed up my color scheme here. There we go. And then I've got no acceleration the whole time, so I'm going to write 0 all the way through. Graphically, what does this look like? I'm starting at t equals 0, 50, then 1 second, 40, 30, 20, 10, 5. And I end up with a constant velocity graph, right? With a slope that represents my negative 10, right? This represents my negative constant velocity, my negative slope. I plot that negative constant velocity over here, negative 10, constant line, at 10. And I plot my acceleration of 0 over here. Okay, let me fix this one. There we go. Okay, and that would be situation number 5. And then situation number 6, we've got x equals 5t plus 10. So if I put in the equation, it would, again, I don't see a t squared term, so it's 1/2 0t squared plus 5t plus 10. What we can see is acceleration is again 0. The initial velocity is 5, right? And so we have a constant velocity of 5 meters per second. All right, going back to these right here, velocities were all negative, right? Acceleration was 0. Here again, acceleration is 0, but velocities are positive. All right, so plugging into this, so x is equal to 5 times t plus 10. So if I put a 0 in there, 5 times 0 is 0, plus we start at 10 meters. If I put a 1 in there, 5 plus 10 would be 15. If I put a 2 in there, right, 10 plus 10 would be 20. And you can see I'm at constantly increasing by 5 meters. Easy pattern. I have a positive constant velocity of 5 meters per second the whole time with an acceleration of 0 the whole time. Okay, plotting this, time equals 0, I'm at 10. So I start at 10, then I'm at 15, then I'm at 20, then I'm at 30, 25, then I'm at 30, then I'm at 35. So I still have a straight line, but it's a flatter slope. That 5 meters per second, right, is my slope. So I have positive constant velocity represented with that slope, and I plot that as a constant horizontal line all the way across at 5. And no acceleration gets plotted as 0 acceleration for 5 seconds. Okay, plotting my points for the motion map, I'm starting at 10, and then my next point is at 15, right in the middle, and then 20, right, and then 25, and then 30, and 35, and then that's it. Okay, and then I have 0 acceleration, so I don't have acceleration vectors, but my velocity should look like this. I should see all my velocity vectors should be exactly the same length pointing to the right. That's showing me good constant velocity. And actually, going back to situation number 5, I forgot to put the motion map on there, starting at 50, right, going every 10 meters like this. Same idea, it's just negative velocity going right to the left, but it's constant velocity. So notice that the arrows are all the same length, but pointing to the left, accounting for the negative constant velocity. All right, so let's fill this out. Look at the 6 situations you have just considered and complete the following general rules. When velocity is positive, the position graph increases. When velocity is negative, the position graph decreases. When acceleration is positive, position graph curves. Now, how does it curve? It curves either flat, it curves from flat to steep. Flat, and by that I mean flat slope to steep slope. When acceleration is negative, the position graph curves again, but this time negative acceleration would be slowing down. So we're looking steep to flat slopes, exactly the opposite. When acceleration is 0, the position graph is a straight line. It's a straight line up, down, or sideways. All right, when acceleration is positive, the velocity graph has a positive slope. Slopes upward, straight line positive. When acceleration is negative, the velocity graph has a negative slope. When acceleration is 0, the velocity graph is a horizontal line, meaning 0 slope. When the object is speeding up, acceleration and velocity vectors point the same way. When an object is slowing down, acceleration and velocity vectors point opposite. They point opposite to each other. All right, now we're going to do some graph matching. We have graphs 1, 2, 3, 4, 5, 6, and then velocity graphs A, B, C, D, E, F. Time to graph position and velocity and match the scenarios, okay? And then finally match them with the description that you see down below. Pause the video, give it a chance, give it a try, then resume the video to check your work. The first thing I would do to do this is analyze the motion in each of the position graphs and then match that to an analysis of motion in the velocity graphs. And when those two match, then you know you've got it linked. So for instance, if I start here with this graph 1, I'm going from flat slopes to steep slopes, right? And anytime I go flat to steep, what am I doing? I'm speeding, but I'm speeding with positive slopes. I'm speeding in the positive direction. So speeding positive, direction's positive. This is positive constant acceleration. Okay? So I'm looking for a graph that I am starting from rest, because I'm starting with zero slope and I'm speeding up from rest. Well, the only one that's showing me speeding up from rest would be graph F. Okay, so F and 1 are going to go together. So let me cross them out as we go. So F and 1 are going to go together. 1 and F. Graph 2. You are going from, again, a flat slope to a steep slope. So you're still going from flat to steep, which means you are speeding up. We're increasing our velocity, but you're doing so with negative slopes. So you're speeding, which is positive, but doing so with negative slopes in the negative direction. This is negative constant acceleration. So which one is showing you you're starting from rest, but speeding up in a negative direction? Starting from rest, speeding up in a negative direction. That would be graph A. So number 2 is going to go with A. Number 3, constant line, positive constant velocity. Positive constant velocity. 3 goes with E. In graph 4, I've got steep slopes to flat slopes. Steep to flat. Okay, what does steep to flat mean? I'm slowing down, which is negative. But I'm doing so with positive slopes. So I'm slowing down in the positive direction. Those two combine to give you negative acceleration. Okay, so I'm starting with a speed and I'm slowing down going in a positive direction. So I'm starting with a speed, slowing down in a positive direction. That would be graph C. So 4 is going to match with C. 5 is showing you negative constant velocity. Negative constant velocity. So 5 matches with B. And then finally, we're going from steep to flat. Okay, so steep to flat, guys, means we're slowing down. Slowing down is negative, but you're slowing down with negative slopes. You're slowing down in the negative direction. Those two negatives combine to give you an overall positive constant acceleration. So I'm looking for starting with a speed, but a negative speed, because it's negative slope, and then I'm slowing down over time. So start with a negative speed, and then slowing down to 0 over time, right, in the negative direction. So that would show us that graph 6 corresponds with D. Now let's take a look at fill out the description so we can match all this, okay? So the first one, the object is moving with constant velocity forward. Again, that would be 3 and E. All right, if you're moving with constant velocity, you have no acceleration. Moving backward with constant velocity. Well, backward with constant velocity, that would be B. That would be 5 and B. That matched. And again, constant velocity is showing you 0 acceleration. Moving forward and speeding up. Forward and speeding up, that's shown in graph 1 and F. And if you have going forward direction, speeding up is also positive. That's positive constant acceleration. Going backward and speeding up. Going backward and speeding up would be number graph 2 and A. And going backward is negative, but speeding up is positive. They combine to give you negative constant acceleration. All right, moving forward and slowing down. Forward and slowing down would be case number 4, right? And that matched with C, if you remember. And so if I'm going forward, that's a positive direction, but I'm slowing down, that's negative change in velocity. Those combine to give us a negative acceleration. And then lastly, the object is moving backward while slowing down. So that would be 6, which matches with D. and backward, both combine, backward and slow down, both negatives combine to give you positive constant acceleration. Okay, so the videos are only going to include the notes and the test your understandings. The examples you leave blank, unless of course you want to try them, but we will go over the examples in class. Okay, so we're going to skip that portion. And let's skip all the way to section 1.7. Okay, now notice right here you have 4 possible constant acceleration equations, but yet again we have more examples. So let's keep moving because we'll do those examples in class. So let's move to page 19 out of 20, which is section 1.8, free fall. Okay, and what is meant by free fall? What does that even mean? Well, here's the deal. Free fall is essentially any acceleration that is caused by gravity. So if gravity caused something to accelerate, that's free fall acceleration. Okay, it is still constant acceleration, but it's constant acceleration due to gravity. Which means variable-wise, your x's become y's. All your x's will translate to y's. And your your acceleration, becomes negative g, which we're going to put in as 10 meters per second squared. So equation-wise, here's what we do. For instance, if we take the equation v equals v naught plus at, what we do is we simply substitute a positive a for a negative g, right? And we need to substitute that, and so we get v is equal to v naught minus gt. So minus g takes the place of positive a. Same acceleration equation, but now we have a constant value of 10 that we're plugging in. Okay, so a couple of things. If it's caused by gravity, okay, to be free fall, there's a couple things that we'll see by this. Number one, the object is slowing down, going upward. Slowing down, going upward. Like a ball being thrown upward, gravity slowing it down. And then opposite to that, of course, would be an object speeding up, going downward. Gravity accelerates and speed things going down. So in both cases, right, that's what you're going to see. Now, the acceleration, the motion again is constant acceleration. And what you have to remember to do, like we did in our constant acceleration, when we have a constant acceleration concept, we have to be ready to list 6 variables: x, x naught, v, v naught, a, and t. Final position, initial position, final velocity, initial velocity, acceleration, and time. And for free fall acceleration, which I abbreviate FA, all we do is just change things. X becomes y, x naught becomes y naught, v is still v, v naught is still v naught, we can still keep the same direction. A now becomes negative g, in which case you're going to plug in 10, okay, for that, but negative g is what we substitute into the formulas. And t is still t. Time is time. Time doesn't have a direction, so that stays as is. What is the value of the acceleration to gravity on Earth's surface? Well, the acceleration due to gravity is called little g, and it is approximately 9.8 meters per second squared. But we'll always just kind of round it up to 10. Right? Now it's negative because it's a downward negative acceleration, but the magnitude of it is 10. Okay, so what we have here in this test your understanding, a person throws a ball upward near the edge of a building as shown. Ignore air resistance and use G equals 10. The first white dot is the position of the ball when it leaves the thrower's hand. Each white dot after that represents the ball's position every second after it leaves the thrower's hand. In the table below, the time represents how many seconds after each ball leaves the thrower's hand. Fill in the speed, velocity, and acceleration for each one. Okay, so I want you to pause the video, give it a try, see what you think you can come up with, right? And we will begin. Okay, now if you struggled with this at first, it's probably because we were lacking some information to start with. So let's try this now. Let's start with velocity. Initial velocity equals 20 meters per second. Let's start with that, okay? Now go ahead and pause the video. Each one, this would be at time equals 0 right here. This would be at time equals 1, time equals 2, time equals 3 seconds, time equals 4 seconds, and then finally time equals 5 seconds, right? Now go ahead and pause the video and see if you can figure out what's happening to the changes in speed and velocity and acceleration as we go through this. Okay, let's see how you did. At time equals 0, we start with a speed of 20 meters per second. The velocity is going to be positive 20. Now, velocity is a vector and therefore has direction. Speed is the magnitude of the velocity and just accounts for how fast you're going. So there won't be any direction for speed. At 1 second, remember, when an object goes up, it's slowing down due to gravity. So what's happening? It's slowing down at a rate of 10 meters per second squared. So we went from 20 to 10 meters per second, okay, to finally 0 meters per second. So our speed looks something like that. Then all of a sudden at t equals 3 seconds, we have the same speed again, so we're back to 10, because we're increasing our velocity, right? We're getting faster. And then finally at t equals 4, it's the exact same velocity as when it left the thrower's hand. It's 20 meters per second. And then finally at t equals 5, we've gained another 10. Now we're at 30. Okay. Now if we focus on the direction of the velocity, for starters, we go from 20 to 10. Now the acceleration technically is negative 10 because you're decreasing by 10 meters per second every second, or you're increasing in the negative direction 10 meters per second every second. Okay, so watch. We're going from 20 to 10, positive, to 0. But then on the way down, since you're moving in the negative direction, you have a velocity of negative 10 because you're going downward at this point. Negative 20 and negative 30. Okay. Pause the video and see if you can fill out this question part right here. Okay, let's see how you did. During which time interval is the object in free fall? Well, 0 to 5 seconds, the whole time. Why? Because the whole time it is under the acceleration due to gravity. We're slowing down going up, we're speeding up going down. When the ball is at 2 seconds specifically, we know for sure its velocity is 0. Why? Because that's the point in which it changes direction. And when things change direction, they have to momentarily stop before they actually change direction. Each second, the ball's velocity changes by 10 meters per second each second. That's how we account for the 10 meters per second squared. The speed is almost the same for velocity, except it does not have direction. velocity does. Fill in the ball's acceleration at each time. We did that. How does the ball's acceleration vary with time? It doesn't. It is constant. Explain how the height of the building can be found. Well, we could use an equation that looks like this. Remember this equation here? X equals x naught plus v naught t plus 1/2 at squared. Remember that? Well, here's how it translates when we're talking about free fall. X becomes y. X naught becomes y naught plus, this is still v naught t, plus a becomes minus 1/2 g t squared. And we simply plug into this equation. Y would equal my initial height of 0, because I'm starting at 0. I'm starting at 0 right here. And I'm ending, I'm ending a certain level below where I started. The ball drops farther than it started. So my initial velocity will be 20 meters per second times the 5 seconds we were moving minus 1/2 of 10 times 5 seconds squared. So this will be 100 meters minus 5 times 25, which is 125. Since the ball, what this number tells you is the ball dropped 25 meters. It fell 25 meters below where it started from, which means the building is 25 meters tall. That would be the height. Okay. In this test your understanding, the table is shown and appears at the bottom of page 30. So pause the book, take a look at that in the electronic textbook, and let's see if we can figure some things out. We have position and time data here, and then we have a different set of time and velocity data here. First question, how are the time asterisks calculated from these time t's here? So how are we getting these numbers right there? And then finally, how are the velocities right here calculated from the times and the positions right here? Pause the video and see if you can figure it out. Okay, t asterisk, this time here, is found by averaging times within a time interval. Now, how are the velocities calculated? Well, velocities, right, if we're talking about velocity as a function of time, then velocities are calculated as v equals v naught minus gt. I hope you found the notes to be helpful. Again, please remember to pause and rewind the video as necessary. Thank you for joining us.